Welcome to this video about climate and topography. They are the main factors forming the environment on our planet. Using climate and topography, we will now show how the environment affects our cities, especially concerning urban form. Topography tries to describe the main shapes on the surface of our world, with the elements of terrain, water bodies, and sometimes vegetation and built structures. This information is usually collected in maps. Depending on the scale, this is more or less helpful for us urban planners. A main factor about topography is the shape of the terrain, its orientation and its inclination. We experience them every day, walking up and down hill, but many slopes are simply too steep to walk straight up them. That usually means they're also too steep to construct on. As a result, the urban layout has to be adjusted to the circumstances, and on a smaller scale, the construction of the building has to be adjusted too. Constructing on a slope brings the problem that the area that is plain and buildable is too small. Further problems can be the lack or excess of sunlight and airflow in the house, and the threat of landslides. Possible solutions for these issues are a plot layout that follows the contour lines of the slope, terraces in the terrain and within the building, and the use of modern construction technology. Moving on to urban form now, we will look at cities in different topographic locations. On a plane surface, there are no outer influences that restrict or shape the urban morphology. Therefore, cities tend to develop a geometric pattern. Often a grid layout is used. In consequence, the city stands for itself and is quite detached from the surroundings. When we look at a city located on a hilltop or mountain, access to the terrain is usually more difficult, and the city is restricted by steep slopes. Viewpoints can also be a factor shaping the layout, so these cities tend to have a strong urban form with a concentric or radial layout, playing with the existing topography. If the city is located in a valley or along a slope, the streets are oriented along the contour lines of the slope, with only few steep secondary streets. Microclimate and topography dominate these kinds of cities. We already saw from this overview that cities are often limited topographically. Here are three examples of cities with either no spatial limitation, located on a vast plain or in water, a limitation on one side, in this case a hill, or several limitations. Here it's high mountains around the city. This has a big effect on the urban identity. Mannheim, for example, has a solitary image and a strong urban form and identity. Morella, with limitations on one side, and its landscape surroundings, they form a new impressionable unit. With several spatial limitations, it can be hard to create a strong image of the city. As we can see here, Innsbruck almost gets lost within the giant mountains. And although the center is very nice, the thing that sticks with you is not the nice city, but the mountains around it. Moving away from the cities for a moment, let's see how agriculture takes different shapes due to the topography. In the plain again, geometric patterns are formed, and due to good accessibility, fields tend to be large. In accordance with the local climate, the crop choice is quite flexible. In valleys, plots are usually a fair bit smaller, and their borders follow the landscape instead of a geometric pattern. Flooding can occur regularly. That can be both a threat to agriculture and a benefit, because in the long term, a very fertile soil is being created. On steep slopes and in the mountains, usually the terrain has to be altered in some way, mostly by introducing terraces. Then it is possible to grow, for example, rice. Otherwise, the produce are oftentimes trees, for forestry or for fruit. Generally, mountainous agriculture areas depend on light and wind a lot. We could see that having plain areas is important when planning spatial expansion, both in rural and in urban settings. In valleys with a lot of water, the problem is that the plains are small and incoherent. To improve land accessibility, it is necessary to reduce the amount of streams and wetlands. A common approach is to straighten and narrow the riverbeds, reducing sidearms, wetlands, and riparian forests. The artificial riverbanks are often elevated to form a plain with the surroundings. Negative effects of this include a higher risk of flooding, the loss of natural habitats, and a worsened microclimate due to the lack of cooling effects. But before we look more into these microclimatic cooling effects, let's look at the bigger picture concerning world climate. The Köppen climate classification describes 5 main climate groups: tropical, arid, temperate, continental, and polar. In a second and third level, these are further divided according to rainfall and temperature. This serves as the base for urban development and urban morphology, as cities have to adapt to these macroclimatic conditions. Looking at microclimatic aspects, we can optimize them on an urban scale, for example with adapted buildings, streets, and plots. Later on, we will consider three important climate elements: airflow, solar radiation, and rainfall. Cities in general are remarkably warmer than their surroundings, a phenomenon known as the urban heat island. Generally, the larger the city is and the higher the population density, the more apparent are these effects. The figure here shows the temperature in comparison to the surrounding areas, with a high increase in the city core and lower effects around the urban green spaces. When we talk about microclimate, we also have to consider the topographic influence on a place. A city in an elevated position has to deal with strong weather influences, such as wind and rain. Situated on a slope or terrace, settlements are either also exposed to rain and wind or sheltered from them. Additionally, the winds tend to be strong during nighttime because of cooling effects, which means sloped places are pretty well suited for cities in hotter climates. The location in a valley or on the base of a slope brings some problems concerning air pollution, as airflow might be blocked. Let us go through an example of a new settlement in Northern Carolina now, to see how climate information can be used in the design process. Due to low winter temperatures, strong winds, weak sunlight, and severe snowfall, three design alternatives were established: maximizing solar access, providing wind shelter, and controlling snow accumulation. The solar solution recommends plots on streets oriented east-west. These guarantee periods of direct sunlight. To avoid the strong winds, a long building for communal activities is placed in the north of the city. The reaction to snow accumulation produces a street pattern aligned along the path of airflow. In the end, the ideal design tries to combine these individual solutions. We would like to introduce single climatic elements and their appearance in the city now, starting with airflow. The picture shows a storm in Tokyo, Japan. Interestingly, we can see in the foreground there's a pedestrian who is bent into the wind, hardly able to walk. Yet in the background, another person can stand calmly, just meters away. This shows how the wind is modified by the structural form of the neighborhood, the street network and the buildings, trees, and even moving vehicles. The urban wind environment affects the city's comfort, air quality, and building energy consumption. Street canyons lined with buildings of similar height oriented against the wind direction tend to form air traps with accumulated pollution. The street canyons lined with buildings of different heights have a better air circulation and therefore a more livable microclimate. In climatic areas with strong winds, stepped or pyramid-shaped buildings and pitched rather than flat roofs can help avoid the negative impact on buildings. The long axis of the building should be oriented parallel to the dominant wind direction. The wooden black forest houses are well adapted to strong winds and big amounts of snow. The roofs have a special shape and almost reach the ground level to protect the insides, while trees in front of the house help reduce the peak wind pressure. In China, there is an interesting phenomenon. In many cities, you can see people holding an umbrella on the street in the summer. Deriving from the pursuit of a white skin color, this also shows the demand for shelters from solar radiation. Here, the mutual shade provided by buildings is considered a useful urban feature, whereas in the Western Hemisphere, homeowners jealously guard their access to a lot of sunshine. Here we see a traditional street in Jaisalmer, an Indian desert town. As a reaction to summer heat and heavy dust storms, all major streets are oriented east-west. The unique street form with a more narrow roof level provides shade at the ground. In the USA, the opposite is pursued: sunshine for all urban levels. After reaching the maximum height that does not affect the sunshine, the building must be retreated according to a certain slope. Taking New York as an example, a conventional shift has happened over the last years. Now the height of the building facade and the difference in the slope of the exposure surface determine the maximum height of the building, and with that, the openness of the street. This approach is suitable for high density and high-rise building arrangements. A high exposure to water can be a threat to densified urban areas. With big sealed areas, the surface has no water absorption function anymore. Many cities are therefore adapting the sponge city concept. One example is Rummelsburg in East Berlin with extensive green roofs, open courtyards between the buildings and underground parking. The soil on the roofs and the garages has a high retention function and acts like a sponge, soaking up the water during heavy rainfall and then slowly passing it on to the plants. To wrap up our video, we'll move from the general urban strategies concerning topography and climate to our project site of Ethiopia to see the chances and challenges this country faces. Generally speaking, Ethiopia has three main topographic regions, each of them with several different climate and vegetation types. The East African Rift Valley divides the Central Highlands into two separate plateaus, harsh mountainous regions with steep valleys and high peaks. The vegetation, however, is lush. Agriculture is possible and the climate is moderate to cool. Due to climate change, the region faces heavy rainfalls causing severe flooding. These highlands are surrounded by vast hilly areas with a mostly moderate habitable climate. Only small areas in the north are desert. Mainly the hills are temperate forests and savannas, many of which are being used for livestock grazing. An increasing challenge these regions face is more extreme weather, including droughts and heavy rainfalls. The eastern plains of Ethiopia are covered by the Somali Desert. This area is extremely dry and flat, and here the constant lack of water has culminated in a severe drought over the last years. Also climatically, Ethiopia is a very diverse country. With a high range in altitudes, several climatic types can be found here. The highlands have a moderate climate with humid and warm summers, here shown in green. The blue areas are humid, hotter savannas, and form very habitable areas too. Orange and red are semi-arid and desert climates, with extremely hot temperatures and a low availability of water. Although the climate is relatively moderate compared to some neighboring countries, Ethiopia suffers from climate hazards. The regular flooding in large areas is a major holdback for urban development, damaging infrastructure, services, and economic activity, as well as impacting urban health. Modern flood protection technologies are highly necessary. The eastern part of the country suffers from a severe drought risk. Extended periods of high temperatures lead to reductions in surface and groundwater supply and limit agricultural crop yields. Food and water has to be sourced from greater distances, which limits and prevents urban development in the region. We can see that multiple climate risks, such as floods, droughts, extreme temperatures, geophysical and landslides, threaten many sectors of the Ethiopian economy. Especially all sectors of agriculture and utilities are severely under the threat of climate change and an increasingly extreme climate. Therefore, how urban systems consider these risks and respond to them through adaptation is an essential component in Ethiopia's national urban strategy to deliver a climate-resilient green economy. I hope you liked this video and we could give you some interesting information to use in our project. Thanks for watching.